Good morning, everyone. Well, it's nice that we're having pleasant weather, and plus you're going to get a short break, maybe to get some rest and relaxation, and then once you've done that, you can study calculus again. I always love the spring term because we have that break. You know, Thanksgiving is really nice in the fall term, or it would be nicer if it occurred earlier. It's like by the time we get that break, it's kind of like past due. But the spring is always a time to rejuvenate and to reassess what you're doing. I always remember as an undergraduate at the University of North Carolina, I was always happier during the spring. And I love the holidays and love the cool weather in the fall, but the spring was always a very uplifting time. I have written up solutions for your test, and I will post those, and I will have some feedback for you by the time we get to our next lecture. So I appreciate your attention to that. I like it by the time we get to the second test, and everything is so much more smooth, and it's just a good opportunity to have a fair assessment, and everything works out really nicely. There's always a learning curve with the first test, so I appreciate your efforts. Now, remember, I've already been teaching you about integral tables. I've thought that it's a good thing to go ahead and teach you about the integral reduction formulas, and also the use of the integral table for special formulas when we were computing an arc length for the quadratic function. So I think you'll find that the integration table will be kind of fun. And I want to show you some things about that. And plus, I want to introduce a very important technique called the Weierstrass technique, which tends to just get lost. So let me go ahead and share my screen. And then after that, we'll talk about something that I know you're going to like, which will be the L'Hopital rules. Uh, Students are always happy to have that technique, even though they lament the fact that it wasn't available to them in Calculus 1. Now, what I want to make aware of you here are the integral table formulas in your Appendix B. If you go to your ebook, it's called Chapter B, and it's integration tables. There are 100 of them. And what's nice is that you can utilize your ebook as a way to actually access these tables, or you can do like Professor Ron did. I do this, since I've been teaching online. I just go ahead and print them out to have them more accessible. But of course, the ebook is fine too, because you can just move between the pages. So when you check your appendices and you work on this, what you're going to see is that you'll have certain forms that are tabulated. And so as you work on a particular integral, you find the integral that matches the form here. And then, of course, we have to make it table ready with the substitution and any adjustments, just like we've been doing. So that's why I'm big on table ready, because I'm referring to the integral table when I say that. So what you can see, and I like to keep these in order, different forms. And what I want to show you, these are some quadratic forms that you can use trig substitution to prove. And of course, here's our famous theorem that we proved with the partial fractions. But I wanted to show you a couple of examples. Again, all these quadratic things with trig sub. And then, of course, these are some rather famous ones that we've already talked about. Remember the reduction formulas. We proved the one for sine, and you used some of these on your last test, and they even have the very famous sine squared and cosine squared. And then, of course, they have certain particular rational expressions of sine and cosine, which we've talked about. And there's one rather famous one right here that I'm going to say more about today, this tangent one. And of course, here's some more reduction formulas and some basic forms. So what this does is just tabulate a lot of nice usable forms. Of course, here, these are the ones that you can prove using integration by parts for the inverse trig functions. And then, of course, if you like, the formulas we've already derived for the e to the au sine b. Remember, I used an alpha and a beta. We proved that in class. That's right here. And so when you take your differential equations course and utilize the Laplace transform techniques, these will be very useful. And then, of course, the last couple, again, integration by parts. Then the hyperbolics, which you learn about in Calculus 1. And then, of course, the forms that are kind of like the companion formulas to the inverse trig forms. So I teach this in Calculus 1, and then, of course, we switch gears a little bit and go to the regular or standard trig function. So I think you'll find that you're already very comfortable with this. But if you look in the literature, the CRC handbook, these are basically the internet of the olden days, where you would have tabulations that went on forever. If you studied chemistry or engineering, chemical engineering, I mean, they were just voluminous. I mean, as an undergraduate, we would go to the libraries and access the CRC handbooks because, again, today, we just use the internet, which is fine. The internet is like the famous Library of Alexandria. The Greeks loved knowledge. They loved learning. It's not surprising because their mathematics output was amazing, even before the invention of calculus. So what I want to do now that I've made you aware of where you can find more information, is to talk about the Weierstrass. Now, I like a lot of times, when I have conversations with you during the conference hours and we talk about conjugate methods. And I remember there was an interesting example. Something went, I guess it was a little like this. I think we had something like 2/3 and we had dx, and then I believe it was secant x minus 1 or something like that. Okay, well, what I did, I've done this problem many, many ways, but when I did the lecture, I actually replaced this with 1 over cosine. Let me just show you just kind of what we did. So you have dx, and then you have 1 over cosine x. You can do this with the secant function. It works just as well. And then, of course, you can multiply and divide by cosine x or just get a common denominator. And so this says 2/3 cosine x dx. And then, of course, the cosine here, upstairs and downstairs, absorbs, and you're left with 1 minus cosine x. Now, this was a very good problem because you could solve it using the conjugate method. And you can go back in your notes and look at this. We'd multiply and divide by 1 plus cosine x. So we do something like this. And I actually wrote this up this way as an alternative form to solving this, maybe in a form that was a little bit easier to understand. But often when we have rational expressions in sine and cosine, or even tangents and secants, we can actually get to an antiderivative using these types of techniques, and they're very useful. And again, we're glad that we have them. However, there are instances when these methods are not available to us. The coefficients don't sync correctly for the Pythagorean identities. We see here that the 1 minus cosine squared that ensues in the denominator is useful because we can replace that with sine squared and then move the problem forward algebraically. But when we don't have all of that, we have to think outside the box. And so I'll just say conjugate method is successful. I mean, let's just face it, ladies and gentlemen, the process of anti-differentiation is difficult. And then, of course, depending on the technique you use, it may take a while to maneuver it back into a form that you recognize, and that's okay. But it's amazing how we take the differentiation process and reverse it, and then impose the mean value theorem, and then it's like, bam, that arbitrary constant really does make things a lot more difficult. So because we know that functions possessing the same derivative differ by a constant, that's the thorn in our side. That's what makes everything difficult. But again, calculus is so amazing, we just really put up with it. So what I want to do now is introduce a technique, and that's why I save time for this. That's why I talk about integral tables all throughout the course, so I can actually spend some time on this. This is a very valuable technique and one that you should learn, kind of like taking Cal 1 and not knowing the fundamental theorem of calculus. We don't want that to happen. When you get out of my Cal 2 course, I want you to know the Weierstrass substitution. So that's what this is. So we're going to look at situations where maybe a conjugate technique or some simpler technique from calculus 1 doesn't work. So often what you'll see in the Larson text is that you'll learn a new technique and then they'll be thrown in an integral where you think you have to use the new technique, but when you stare at it, it's like, no, 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 that's an easy one. I can do this based on the techniques we've already learned. So we don't want to take out the major artillery unless we need it, because it's too much work. So here's the substitution. So Weierstrass was a German mathematician, and he did a lot of work with Bolzano. There's a very famous theorem in real analysis called the Weierstrass or Bolzano-Weierstrass theorem. And basically it says every infinite set of real numbers contains at least one limit point. Now that sounds simple, but it was an amazing result and is used ubiquitously now. So again, we are grateful to Newton and Leibniz for pushing all of the calculus out and finding the connection between the derivative and the integral. But it's all the German and French mathematicians that followed them that really brought the calculus to a level that we could understand. And of course, we're indebted to Leibniz for all the great notation. Now, here's the substitution. For instance, what we're going to do is assign our favorite variable. And I'm sorry I use u all the time, but it seems to be the variable of choice. And what we're going to do is set this equal to the half angle formula for tangent. Now, when you took pre-cal, of course, if you have my class, I beat this to death because I know you're going to use it in calculus. And so you should have already seen this, but the form that we enjoy is the rational expression in sine and cosine, right? How fortuitous. It's like, well, that's where we're headed, right? So the form that's actually pretty simple to prove, and I call this the remarkable formula because it has no radicals in it, which is somewhat amazing. So this is an identity from trigonometry. And I just call this, and really, I guess with Weierstrass, this is called the remarkable formula. Now, when you think about it, it's like, do I have to do, square roots, plus and minus, the power reducing identity? The thing is that, with the cosine of the half angle and sine of the half angle, you are stuck with the plus or minus radical. But somehow it's disappeared with the tangent, which is not surprising if you think that tangent's the ratio of sine and cosine. So you're thinking, okay, I think I believe this, but what would be the quickest way to show this? And then we're going to apply some algebra to this and then some calculus. So the idea is why? Now, the sad part is that you get to, you get your brilliant students in calculus 3, and you ask them to prove this, and they just scratch their head and say, well, Professor Wright, I didn't prove anything until I got to your class. I said, okay, well, let's start. So what we can do is work backwards with the double angle formulas for sine and cosine. So we know that sine of x is just 2 times sine of x over 2 cosine x over 2. So we can think of x as the double angle and half of it is x over 2. So it's just a reworking of the double angle formula. And thinking about this, we can think of cosine x as 2 cosine squared x over 2 minus 1. Again, using the form, remember cosine of the double angle is the cosine squared minus the sine squared. And then, of course, you can replace the cosine squared, you can replace the sine squared with the 1 minus cosine squared, and then get 2 copies of the cosine squared. Now you're thinking, oh, I see what you're doing now. And now you can see that this formula has already fallen out. So that's why I enjoy doing this in calculus. Sometimes I put more time into it, but it's just this simple. So now we can see that if we look at sine of x, and of course transpose the 1 plus cosine x, we just get 2 sine x over 2 cosine x over 2. And then, of course, we're just left with the two copies of the square, which we'll write in linear factors. So this is like a pre-calculus exercise. My pre-calculus kids get this, but of course, by the time they get to calculus, they pretty much forget this, but that's okay. If they've seen it before, there's a higher level of understanding. So now the cosine of x over 2 of the half angle, these terms absorb, the 2's absorb, and we're left with sine of x over 2 divided by cosine of x over 2, of course, which is tangent of the half angle. So that is probably the simplest way to go about an effective proof of this, even though I would say that however you come about it, it is still good. This just happens to be the most efficient. What you're finding in calculus 1 and 2 is that the calculus is supported by the algebra and the trigonometry, and the difficulty of calculus is in the mechanics. It's not usually in the intuition. You do have to develop some finesse with the new ideas, the new constructs, but it's the manipulations that are difficult, and trying to synthesize everything you learned before into the calculus problems. So the calculus sequence is one of the most growing experiences you'll have in mathematics. And then after you get out of this sequence, any other math course you'll take, you'll find yourself going right back to calculus to undergird what you do. So how does this help us? Well, now if we see that the half angle formula of tangent is bound up in a rational expression of sine and cosine, Weierstrass saw that this particular substitution would turn out to be very useful. And his genius is that he would convert the rational expression of sine and cosine into a rational function of u. So here's what he does. So we want to solve, and I'll just, again, this is the equation. We're going to solve everything in terms of u. So now u is the half angle formula for tangent, but it's also this rational expression. So solve for sine x and cosine x, and then compute the differential. So basically what we're going to do, when I say the differential, well, actually, it's going to be bound up in du, but we're going to think we're starting with a function in x, so I'll just say dx. So we'll start with something that looks like this, or maybe the formula is theta, and that would be like a d theta. But we start with this and then convert to this. And if we actually can make this algebra happen, then we can take the formulas to do a conversion into a rational function and possibly apply partial fractions or whatever technique is available to us. Maybe we don't have to do something that complicated. So now, when you look at this, we can just square both sides. So this is some simple algebra here. So square, hook or crook. Again, this was ingenious what he came up with. So u squared equals sine squared divided by 1 plus cosine x squared. So I did this simple proof here to kind of give you an idea of how we're going to work here. Now, what he realized is that in order to affect a solving for cosine, the first thing he's going to do is replace the sine squared with 1 minus cosine squared. You think maybe he had a dream about this and just woke up. You know, it's kind of like Fermat and the famous last theorem. He solved it in his head, but didn't bother to write it down. And I really do think he probably had a proof of some sort in his mind, because he was considered to be one of the greatest mathematicians throughout our historical period, on the level of Newton and Leibniz and even Gauss. So now when we look at this, we see the difference of two squares will absorb one of these factors. So we get 1 minus cosine x, 1 plus cosine x, divided by 1 plus cosine x quantity squared. So equivalently, again, one of these absorbs, so we have u squared equals, in this case, 1 minus cosine x divided by 1 plus cosine x. So now we're just left with one copy of 1 plus cosine x, and that, of course, has absorbed. And now we can cross multiply like we're in college algebra, when that was something I could always depend on for my students. So when we cross multiply, we get u squared plus u squared times cosine x equals 1 minus cosine x. And these formulas are in your text. I'm glad when I hear that you all are reading the text. You should. I ask you to do that in your weekly assignments. The book is good. It's an excellent book. That's why we use it. And you can always get new perspectives and ideas. So enjoy the book as a additional source of knowledge, and also as a primary source. So now we can isolate all of our cosines on one side. So let's just take this over. So we have cosine x. So that'll give us a u squared. And of course, if we bring this over, we'll get a positive 1. And now, of course, we can subtract the u squared from both sides and get 1 minus u squared. And kind of like the inverse tangent form, it's conventional to write the 1 first, even though that's not descending order. So cosine x equivalently. So now we get a rational function in terms of u will be 1 minus u squared times 1 plus u squared. So this gives us a formula for cosine, a rational expression in u, which is an improvement. Again, you would see why we would not want to do this technique, or at least what is appearing to be this technique, when other simpler strategies are available to us. Because this, I mean, it's not overly difficult, but it does take time. So now let's use this to get a formula for sine x. So now, in summary, that is, we know that u equals sine x over 1 plus cosine x. But this is good because we already have a formula for cosine x, so we'll just go ahead and substitute. So this will be easy. So this will be sine x divided by 1 plus 1 minus u squared divided by 1 plus u squared. So we just derived that. And so now we can get a common denominator. So we have sine x. So we have 1 plus u squared. So this will give us a 1 plus u squared plus a 1 minus u squared, just with the common denominator in the denominator. And so now, of course, the u squareds absorb, and 1 plus 1 is 2. That's what my students used to say. Can we do 1 plus 1 is 2 today, Professor Ron? I said, no, we have to rise above. I said, even though that's very important and we rely on it. But you know, ladies and gentlemen, if you actually prove that 1 plus 1 equals 2, set theoretically, it would be undaunting. I mean, it would be daunting. I mean, read the Bertrand Russell Principia, and you'll see that after he wrote that work, he kind of lost his mind because it was taking math back down to set theory at the very basic level. So now we can just say sine x will be 2 times 1 plus divided by 1 plus u squared times u, so we can cross multiply and just leave the fraction downstairs. So sine x equals 2u over 1 plus u squared. So there we have it. And okay, I'm just gonna go ahead and write down the formula. Well, that's the formula for cosine x, to just have it right beside 1 minus u squared, 1 plus u squared. Now you're thinking, what about the differential part? And that's really the easy part. And maybe I should have started with that. But again, I wanted to go ahead and do the algebra to get these. And of course, if you wanted, and you know, you're thinking, well, if we just took the ratio of sine to cosine, the 1 plus u squares would absorb. So we could automatically get a formula for tangent, just for free. Tangent x. So again, the 1 plus u squares would absorb, and we just have 2u divided by 1 minus u squared. So that's a freebie. That's usually not written down, but I was working a problem that utilized this technique, and it turned out to be rather wicked, but of course it's okay. So here's a little aside. To just get plain old tangent, just take the ratio. Again, these absorb, and we're left with 2u divided by 1 minus u squared. Now, for the last part, remember u equals the half angle formula of tangent of x over 2. This is a good derivation to know because you might find yourself confronting these types of integrals and need a little bit more background. I mean, you can always look in a calculus book or whatever, but if it's not available, this is something that's not too hard to remember. So now you can see if we need dx, we can just apply the inverse tangent to both sides of this equation. So x over 2 will just be the inverse tangent or arc tangent of u. And then, of course, we can cross multiply by 2. So x equals 2. So what are we doing here? This is miscellaneous substitution. We saw that trigonometric substitution is a miscellaneous form, okay? You completely transform the integral. I mean, it's not your basic substitution, make it table ready and adjust it. It's just a complete reworking. And that is the amazing part of the integration process when you think about it. It's amazing that we can make these substitutions and transform things, hopefully, into something that's easier. So now we can take the differential. We know how to differentiate the inverse tangent. So this says dx equals 2 times 1 over 1 plus u squared du. So good for us that we know this. So equivalently, we just move the 2 over. Dx is 2 du 1 plus u squared. So even though this is a little extra, as long as you have rational expressions in the first power of sine and cosine, then you can use these substitutions along with the dx to transform the integral into a rational, or integrand into a rational function in u. So that indeed does provide a simpler integrand. The idea is, however, we don't want to apply this when it's unnecessary. The idea is look for du over u, look for a conjugate technique. It'll be fairly clear when it's not going to work, but you might be surprised a lot of times. This is why I address this in the preliminary review of the Calculus 1 techniques, so that now you can see why this is actually important, and it ends up in integral tables. My colleague Nate Wiggins, I used to put problems like this on the whiteboard in my office when we actually were on campus, and I had a whiteboard, and he said, oh, we use the integral table for that. And I said, well, did you do the Weierstrass? And he said, I don't know. He says, that's too complicated, but we laugh about it. He says, well, sometimes I do it and sometimes I just, use it as an example for the integral table. But the algebra here and the calculus here is really nice. And it's a good thing to promote your understanding by allowing you to see the difference. When you really do need, for instance, when you use an integral table, you might be thinking, I could do this myself. But here's the thing, the integral table is quick and efficient. So a lot of times, as an undergraduate, when I would use an integral table, I would think, well, how would I do this if I didn't have the integral table? In some cases, very straightforward. In other cases, I'd have to say, okay, if I got to justify this or prove this, then I may have to set up integration by parts. I may have to set up, partial fractions, and do those techniques, or a trig sub. So the thing about the integral table is it summarizes nice integral formulas that usually, if you're fairly adept at doing integration, you can justify. But the whole idea is to give you a quick access to the antiderivatives to quicken the process. So that's all it is. And that's what my colleague was suggesting. So again, it's kind of a give and take. So let's look at some examples of this where we actually use this technique. So here is our game plan, so to speak. So let's use our game plan. This is in your notes, just write the following: Weierstrass substitution. So now we know what it is. I talk about it and I play it up like it's wonderful, and maybe it's not as wonderful as you thought, but it is kind of amazing how it works. So now let's look at some examples of where we can use this. So here's the first example. It's a definite integral. So we have the integral 0 to pi over 2, our favorite integral, Professor Ron, on the test, 0 to pi over 2. Everybody like that, I'm sure. So just remember that when it comes to testing and all, it's always using everything you know. And I'm always glad to hear when students get in touch with me and say, Professor Ron, I was more consistent with this test and it paid off. And I said, you know what? That's great. That's great news, because the consistent effort is a method for the future. It always pays off. And don't we know, even though life may sometimes get in the way, and we know it does, just taking that time to put in a little effort, some days a lot of effort and other days not so much, builds that confidence, you know, because we have to do it. We don't like marathon studying. That just stresses us out. Sometimes that's all we can do. But I hope that you're seeing a difference in the consistent studying and how it rewards you in your mathematics. Now, when you look at this, you're thinking, well, the conjugate method is really not available to us. We have a trinomial downstairs. And so we don't really have the luxury of being able to say, well, let's multiply by, you know, 1 minus cosine x or 1 minus sine x or something of that nature. So here would be an example where we really don't have a calculus 1 technique. So this would be a good example for Weierstrass. So just like I had before, we just take out our substitution and transform the integral. So remember now as we do this, since we have a definite integral, u is tangent of x over 2. So when we do our change of variable for the limits, we need to use this substitution because it's bound up in this. So that's why all of this is part of the process. There's nothing here that's unimportant. So now let's go ahead and check our limits. U of pi over 2 will just be tangent of pi over 2 divided by 2. Well, you know, back to the unit circle. Very nice. So that's tangent of pi over 4, which is our friend, which is 1. And then, of course, u of 0 is tangent of 0. And we know that to be 0. So we've got new limits, lower limit of 0, upper limit of 1. And we're like, yay, you know, what's the best, what are the best limits to have? 0 and 0, right? But a lower limit of 0, upper limit of 1, how simple is that? But of course, now we have to kind of pay for all of this beauty, right? 0 to 1. Now let's go ahead and substitute for d theta. This will be 2 d theta, excuse me, du, sorry. Remember now we started with theta instead of x. So at this point, the d theta will be this. So 2 du, 1 plus u squared. So remember, whatever variable you have here, it doesn't matter. It could be x, it could be theta, it could be z, no big deal. Then we have 1 plus sine theta is 2u, 1 plus u squared. We see the 1 plus u squareds will eventually absorb, so that'll make things a little easier. Plus 1 minus u squared divided by 1 plus u squared for the cosine term. So again, the sine x here, or sine theta, will be 2u over 1 plus u squared. And the cosine theta, like we have here, will be 1 minus u squared over 1 plus u squared, right here. So now let's clean it up a little bit. So we have 0 to 1. We just have to do the algebra, and that's the only part that just, you know, we do like we're in an algebra 2 class. So let's get a common denominator of 1 plus u squared. And so here this gives us a 1 plus u squared plus 2u plus 1 minus u squared. Now we can see that these absorb. You don't have to invert and multiply. You can easily see that now upon inversion and multiplication, this would just come upstairs, this comes downstairs, and they absorb. So these absorb. So what does that leave us with? Okay, well, upstairs, we have a 2 du. And downstairs, notice the u squared terms absorb. And we're left with, and here's another thing too that you notice I left out my extra one here. That's important. The 1 minus u squared. That's why math is the most rewarding thing. If you leave out a word in a sentence, it's the same thing. You say, oh, I'm typing a email or typing a paper or something. Oh, I need to do this. Math is the same way. So now notice the u squares absorb and we have a 2 plus a 2u. So we have 2u plus 2. So sometimes when we do the Weierstrass, we get a really nice simplification. That is, we really do reduce to a form that is really, really straightforward. That doesn't happen all the time. However, we may find ourselves having to use a formula that we've already derived or usually partial fractions, because when you look at this, you're thinking, well, when we reduce this, we're gonna have a reduced expression in u that's rational. And so that opens the door to partial fractions. So now notice the twos just go away. They all absorb. So this gives us the integral 0 to 1 du over u plus 1. So again, all of these absorb. 2 over 2. But now this is a very simple integral, essentially du over u, the substitution u plus 1. So this gives us the natural log of u plus 1 in absolute value, 0, 1. So this gives us natural log of 2. We substitute 1 for u, and then when we substitute 0, we get natural log of 1. And of course, this is 0, so we can just write natural log 2. And of course, it's okay to write it this way, but of course, in your WebAssign, you'll be closing that. It's just like doing, for instance, here, if I do tangent of pi over 4, that's clear because it's a fraction, but you can always put that in parentheses. So now what we're seeing is that once we apply the Weierstrass substitution, we see that the process is at least algebraically straightforward. That is, what's the catch? Well, the catch is that, again, like I say, we started with x. Here the variable's theta, so we just think of theta instead of x. No difference there, obviously. But what we see is that when we use this substitution, we make formulas like this doable. And then of course, these make good candidates for integration tables, because this substitution can produce lots of formulas. So you'll see these formulas set up in integration tables. So the thing about this is that as we learn a major technique, for instance, like integration by parts, you can use that to prove all kinds of integral formulas. And we've already seen that in action. Partial fractions, the same thing. Those are two major techniques, trigonometric substitution, that push the integral tables to the limit, so to speak. So again, now you can see that this integral is quite accessible with our new substitution. Let's try another one. The next one, again, I just made this one up. I thought we'll do something interesting. The problems are fun, and just remember that when it's all said and done, we just work out the problem using techniques we already know. So I thought I would just jazz it up a little bit. So here we have 0 to pi over 2, and I actually took a formula that you see a lot, like in your WebAssign, but I threw the limits on it. So this is a 3, and of course we'll use a theta again. It's good to use a variable that we don't always use. Just think of the theta just like when I was using x at the beginning. So now we're thinking in this particular case, notice here, when we go back to this problem, I was thinking X, so of course that should have been the theta there because we're using theta here. So yeah, that was it. I'm sure you all noticed that. So if we're going to do that, then we need to make sure everything is precise. So we all get stuck with our same old variables. It doesn't change anything, but you know, things do need to be correct. Even if it doesn't change the outcome, it's still important. So now when we look at this, we're thinking, okay, well, we've got theta here, d theta. And of course, this would just be a nice antiderivative formula. That is, if there were no limits. And I've done the problem. I think when you look in your lecture notes on Blackboard, you'll see something like this computed. So when we look at this, we're thinking, okay, well, this doesn't open the door to the techniques that we used before, basically because of these coefficients here. We have a 3 and a -2, so that doesn't open the door to the Pythagorean identities. Kind of like what I was talking about with the trig sub. When you start getting these interesting coefficients, the Pythagorean identities don't work anymore. If you can't extract common factors to free up a 1 minus a trig function or something of that nature, then the trig sub doesn't work. So here's a very good example of that going on. So now again, remember, and I'll use theta this time, we have u equals tangent of theta over 2. So let's go ahead. We already know what the limits are. Let's just write them down. U of pi over 2. We've already done this. This will just be tangent of pi over 4, which is 1. And then, of course, u of 0 is 0. So we want to transform this. So we're going to get 0 to 1. And so now, if you like, we'll just go ahead and put the 1 here. We'll put the d theta off to the side just for, just to change it up a little bit. So first, let's go ahead and write this in. So we have 3. Now notice again, this is less busy and we'll get common denominators, but the 3 and the -2 will make more arithmetic. So we have -2. And then of course, we have our substitution for sine, in this case, 2u over 1 plus u squared. And then, of course, we have 2 du over 1 plus u squared. So again, the differential 2u 1 plus u squared. So, just put these on the note card with all your other famous formulas, so to speak, to have these available. You use them enough, you'll remember them, but it's always good to do a once over. So now, of course, we can see that we have levels of, when we invert and multiply, these 1 over 1 plus u squares will absorb. So let's just go ahead and get a common denominator and wish them away. So we have 0 to 1. And if you like, you can just go ahead and move this upstairs so it looks like the other one. 2 du 1 plus u squared. So just move this over and it'll mimic what we did before. And so we have 3 times 1 plus u squared minus, now we have 4u, all divided by 1 plus u squared. So now, just like we had before, the 1 plus u squared denominators absorb. So these absorb. So this leaves us with the integral 0 to 1. So now we've got the 2 du by itself upstairs. And then downstairs we have a 3 plus 3u squared minus 4u. Now, when you look at this and you think about what we need to do here, we're thinking, well, we're back to this complete the square deal. So this gives us the integral 0 to 1. Of course, we can factor as we need to. 2 du, 3 u squared minus 4u plus 3. So when you get to a form like this, let me check the focus. When you get to a form like this, you're thinking, okay, we're back to the properties that we used on the very first day if we needed to complete the square. And so when we look at this, we're thinking, okay, well, maybe we can force an inverse tangent, or maybe we can do a partial fraction decomposition if we get a minus or something. So now we're thinking, okay, complete the square. So at this point, we've reduced this to this, which is manageable. So we'll say complete the square. And we don't have to be very fancy with this. A lot of times when we're doing a definite integral, we don't have to always make it look as beautiful. So in this case, we have the integral 0 to 1, 2 du. And so we just focus on the first two terms and then add whatever riffraff we need. So we need to make this monic. So this will be 3 times u squared. And then, of course, we have a minus 4/3 u. Again, just factor the 3. And then, of course, give us some space, right? Plus a 3. Now, remember, at this point, we take half of this coefficient. So I'll do this in right here. So take half. So this will be 4/3 with a negative times a half. I mean, this is easy. You know how to do this, but I'm just focusing on the obvious. So now we just get what? A negative 2/3. In this case, the 2 absorbs into the negative 4. So negative 2/3 squared, which gives us a 4/9. So we add and subtract that. I mean, you can do that in your head, but it's good to write it down. Of course, if we write it down, we have something to check. So now we have a perfect square. So we have 0 to 1. Now we have 2 du. And of course here, this is our perfect square. And of course, that's the term that we need by the u. So this will be 3 times u minus 2/3 quantity squared. Again, when we square this, we get the 4/9. U times negative 2/3 times the 2 gives us this term, and of course the u squared. And so of course here now, when we multiply, the 3 absorbs into the 9, so that gives us a negative 4/3. And if you like, just write the 3 as a 9/3 so we can easily affect the common denominator. So this is very simple, but good old calculus 1 techniques. So T du. So we have 3 u minus 2/3 squared. And then of course here, 9 minus a 4 is a 5. So we get plus 5/3. Now, this is exactly what we wanted. That is, we wanted something that was going to remind us of a form we already know. This is the inverse tangent, but we need to get rid of the 2/3. I don't want to go ahead and pull that into the radical. Just go ahead and factor the 2, factor the 3, and we're good to go. So we'll deal with that. So now this will give us 2/3. So now we're back to day 1 of the class. Du. And so now, of course, if we factor the 3 out of this, we've got to pay for it here with a multiplication by 1/3. So that's 5/9 plus u minus 2/3 quantity squared. So this gives us the inverse tangent form. And of course, if that were the substitution omega, then du equals d omega. So there's no adjustment necessary. And of course, the a here is going to be the square root of 5/3. So we can say at this point, a will be the square root of 5 divided by 3. And we can say omega is u minus 2/3 and d omega is du. So no adjustment necessary there. Of course, I can't use u because I'm already using it. So now, so let's just look at this. We think about what we're doing and we see that with this substitution, we do effect a rational expression in u, and then we apply a technique that we already know. So the idea here is that, again, this is much simpler than this. Otherwise, we just stare at this. So now, remember, we've got the 2/3, and then we need 1 over a. So that's 1 over square root 5 divided by 3. And so we have inverse tangent. So we have u, didn't make it look very beautiful. Just keep it nice and simple. And so in this case, we divide by a. So this would be the square root of 5 over 3, 0 to 1. Remember, u over a, 1 over a outside. So let's clean this up a little bit. So now this is 2/3 times 3 over the square root of 5 when we reciprocate that, so the 3's will absorb. So inverse tangent. And now the 3 comes upstairs, so we get 3 times u minus 2/3 over the square root of 5. Yeah, when you make them up, they're not as beautiful, but this is what happens in physics and engineering. You need to be able to deal with the messy numbers. So now the 3's absorb, and we get 2 over square root 5. And so now when we substitute 1, that'll be the inverse tangent of, so substituting 1 will give us 3 times that, well, we got 1 minus 2/3, so that's a 1/3 divided by square root of 5 minus inverse tangent, or arctan. Now, when we put in the 0, we just get a negative 2/3. So that's a 3 times a negative 2/3. 3 times a negative 2/3. And of course, the inverse tangent is odd, so we can factor the negative. That's always a nice quality to use. So this gives us 2 over root 5. And then, of course, here the 3's absorb. So this is inverse tangent, or arctan, of 1 over the square root of 5. And then, of course, here the negative will factor to give us a plus. And so that just leaves us with a 2 over root 5. So now what we see is you really never know what's going to happen with the Weierstrass. And like I say, I like to sometimes throw in limits just so we can practice the fundamental theorem part 2. But notice the technique here, this makes a great test 1 problem right here. I don't, it's certainly no more difficult than problems you all have done many times. The idea is that at least we were able, with the Weierstrass substitution, to transform this integral, which was a rational expression in first powers of sine and cosine, into something that was reasonable. That is, we see at this point we are good to go. We either we're going to get something irreducible. We can apply a formula from the integral table. We can apply partial fractions, whatever. We found it very nice that we ended up with the inverse tangent form. And again, just remember, you need an a and you need something squared. You need the a squared plus the u squared. Okay, and so you don't have to make the expressions look overly beautiful, especially when you're doing the definite integral. So what's nice about this, very accessible, nice exact answer, which is what we always want. Again, as future STEM professionals, you need work that's clear and clean. And this provides another technique. So I hope that this technique is is at least giving you the idea of how we produce formulas for the integral table and how we take what we know with a particular miscellaneous type substitution. Remember before, when we'd use miscellaneous, it was usually when we were trying to eradicate a radical. What did we get with that? Well, when we did that, we get a rational expression in U. Okay, but most of those particular examples could be done with techniques that we knew at the time, and then of course, if it required integration by parts, we saw how that would be very useful. So with this, we've already introduced partial fractions, so we see that that may be a possibility, but so far we've seen that the use of du over u finished the problem for us. Here, the use of inverse tangent form finished the problem for us. So no problem is set. You can't look at it and say, well, I'm going to get this. I think I might get this. You can look at the algebra and say, well, it looks like I'm going to get this type of expression. So all of these techniques hinge on the previous techniques. And as you look at the integral table, kind of think to your mind, in your mind's eye, how would I actually justify this? You know, like Professor Ron used integration by parts for the integral reduction formula for sine to the n. Think about what technique you might use. Again, as an undergraduate, the professor would say, okay, take out the integral table and prove this formula. And we're like, oh man, you don't want to reinvent the wheel every time. And so of course, when you're in your engineering classes and your physics classes, you'll use your integral tables and be happy to do it. Now, there are more examples, but I want you to go ahead and get used to this technique as I've displayed here, and then I may have time to go back to that kind of unfortunate problem that I came up with yesterday. I was looking at the integral table and I said, "Oh, that looks like a great Weierstrass substitution." And yeah, it was pretty wicked, but I think I'm going to save that. I let this sink in and let you work with this a little bit. That might be a little better way to go about it. Now, with the integral table, there'll be lots of interesting examples that you can work through, and they're not difficult. Again, I've already used the integral table in the problems that I've done, so I want you to go ahead and practice with that. You will not find that difficult. Now, so what we want to do now, again, we're still going to do some more integrals with the improper integrals, but what I want to do first is give you an introduction to L'Hopital. Now, when you took Calculus 1, some of your classmates might have said, well, I wish we could use L'Hopital's theorem or whatever. Maybe you had taken or they had taken an AP calculus course and they were familiar with it and said, oh, why do I have to do all of this? So for what it's worth, knowing techniques that make you better mathematically are important. And then knowing when you can use a more significant result that you can use it legitimately is also important. So let's talk about a way to compute limits that might make your life a little bit easier. And of course, I keep going back to the transform methods, ladies and gentlemen. When you do transform methods, you are often required to pass to limits. And so it's important that we have these techniques. That's why Calculus 2 and Calculus 1 form the bedrock of the class differential equations. And then, of course, you even use some multivariable techniques, which are usually just taught in the class. If you have not had Cal 3, it's not required. But again, when you get to solving equations that actually have differentials in them, you need the calculus, obviously. So the Cal 1 and the Cal 2 really are the cornerstones of the classes that follow. So what Dr. Larson did was kind of crazy. He stuck this back in chapter 5, which at the time when the publishers mentioned this, I thought, well, why are you doing this? Well, every time you think about rewriting your book, you push things around, and that's fine. But we still reserve this for calculus 2. So this is called L'Hopital's theorem. And there's a lot, if you look in the notes, I've worked through some arithmetic arguments that are fairly complicated. I always have that available to you if you're interested, but I will not test you on that. That's more of an advanced calculus field that you would talk about. And of course, when I do an honors section, the students have to learn some of those techniques, but in the regular section, we'll just focus on being able to understand when it's applicable. But if you have the extra time, look through some of those arguments. They're interesting. And, like I say, I wanted to spend more time on the Weierstrass because I think it's a really important technique. So I have to juggle things too. So this is what we call indeterminate forms. Now, the idea is that for right now, we're going to think of forms that we encountered in Cal 1. So here's what we'll have. We'll say, suppose F and G are C1. That is, they have continuous derivatives, just like when we did arc length. Of course, when we get to Taylor's theorem, we're going to need Cn, or we always need continuous derivatives if we want to have a nice theorem. Otherwise, we're stuck. So C1 in an open interval containing C. Now, there are other versions of this that we will actually adopt, but here's the main version, containing C. If f of C divided by g of C has an indeterminate form, like we're doing derivatives, like you have 0 over 0, or f of C divided by g of C, say these are infinite discontinuities, we get infinity over infinity. Or any sign convention of that. That is, we could get a plus or minus infinity upstairs and a plus or minus downstairs. So we'll just say plus or minus infinity does not change the mathematics. We'll say either of these is acceptable. So this is what we call the basic indeterminate forms. That is, when you're doing derivatives in calculus 1, you look at the difference quotient and you're like 0 over 0. And then you're thinking, what do I need to do? Oh, I need to get rid of the h, or I need to get rid of the delta x, because I need to prove that the numerator gets to 0 faster than the denominator. That's really what you did in calculus 1. And if that weren't the case, then the limit didn't exist and you had no derivative. You had a corner, you had a infinite discontinuity or an infinite tangent or something. Obviously it was continuous. You were computing a derivative. It would make no sense otherwise. But the idea is that you've already talked about indeterminate forms. And then you might have been looking at rational expressions, where if you looked at the numerator and the denominator, they became infinite, either positively or negatively. So L'Hopital specifies these two indeterminate forms. Now, it is going to be possible to have other forms that we can rig to look like this. So when we apply L'Hopital, we must be able to rig one of these forms. Whatever expression that we determine and we apply the limit, either we're letting x approach c, or maybe even x is approaching infinity. We might even look at limits at infinity. If we're going to apply L'Hopital, we've got to have these forms in tow. Otherwise, the theorem does not work. So then the limit as x approaches c, and of course we can do right and left limits. We can be real flexible here. F of x over g of x equals, and this is the key to the theorem. This is the amazing part of the theorem. This will equal the limit of f prime of c, f prime of x. We want to pass to the limit first, Professor Ron. G prime of x, provided the limit exists. So when you think about difference quotients, this is actually very doable. And if you look at my notes, you can see that it's a very reasonable result. So the idea with L'Hopital is that if you have one of these forms, I mean, you can't, okay, 0 over 0, what is that? You don't know, it's indeterminate. Infinity over infinity, or some combination of that sign-wise, you don't know what it is. It's indeterminate. So L'Hopital's theorem allows you to differentiate the numerator and differentiate the denominator. Note, this is not the quotient rule, okay? Please do not confuse that. This is basically saying differentiate the numerator as a single function. Differentiate the denominator as a single function. Apply the limit. If this limit exists, these are equal. That is the beauty of this theorem. If this limit exists, then it equals this limit. So you're thinking, wow, that's a major result. That takes something that I don't even understand into the realm that we do understand, and we're done. Now, another thing that's important, if this is still indeterminate, you can reapply L'Hopital until you get a limit. It's kind of like you just keep applying it as long as it's legal to do it. And if you get a limit, you're done. So important is that this result can be reapplied. And it is also valid. Reapplied as long as the results here are in tow. And it is also valid for limits at infinity. The key here is that if you can achieve the indeterminate forms here with the C1, then you're good. So you may find that you might have to apply L'Hopital 2 or 3 times before you actually get to an actual existence of a limit. And then you can run everything backwards to the very initial limit. You know what it is. And of course, all the ones in between. So when Calculus 2 students hear about this and they're thinking, are you serious? Oh my goodness, why couldn't we do this in Calculus 1? But think about it, ladies and gentlemen. When you learn limits for the first time, the limits precede differentiation. So you don't have this available to you. So the key is to teach students about the arithmetic of limits and then move to differentiation and then hold off on L'Hopital for Calculus 2. So let's look at some examples here. So you're going to like this, and let me just let the cat out of the bag. This is a whole lot easier than integrals. So this gives you a little break. You know, maybe you got weary of all the integrals. So let's look at this. We have the limit as x approaches 6 of the square root of x plus 10 minus 4 divided by x minus 6. Now, lots of times in textbooks, they'll say, well, use your calculus one techniques. That is, if you looked at this, you might be thinking, well, I could apply a conjugate technique if you were looking at this and thinking, because now if you just say, okay, what do we learn in calculus one? If the function is continuous at 6, we just substitute, we're done. Okay, well, so we look at this and see that we have what? 6 plus 10, that's the square root of 16, which is 4. So 4 minus 4, 0. And then, of course, 6 minus 6, 0. And we're thinking, okay, well, that's indeterminate. So we look at this and say, this is indeterminate. It matches that. And of course, in a neighborhood of 6, these functions are nice and well behaved. They're C1. So now we look at this and say, okay, well, back in Cal 1, we would have done the conjugate technique like we do with the trig functions with the integrals. But now, if you want to do that, fine. But now we have the luxury of L'Hopital. So let's do it. So we can apply L'Hopital. Usually I'll just say LH for L'Hopital. So we'll take the limit as x approaches 6. So we'll just apply the derivative upstairs and downstairs. So this will be 1/2 times x plus 10 to the negative 1/2. And of course, the derivative of the minus 4 is 0. Very simple, really too simple. And then, of course, the derivative downstairs is just 1. So this gives us the limit as x approaches 6. And of course, we can just rewrite this, just take everything downstairs if you like, 2, and factor the 2 if you want, square root of x plus 10. So you're thinking, wow, isn't that nice? That's a very, very nice use of the theory. And so now we're thinking, well, this is continuous at 6. So I can just substitute. So now this will equal 1/2 square root, apply the 6 or substitute. So this is square root of 16. So we have 1/2 times 4, which is 1/8, which would have been the same answer you would have achieved using the conjugate method. But now that we're in calculus 2, we can use L'Hopital. And you will find many, many uses of this theorem, especially in physics and engineering. It is ubiquitous and one of the cornerstones of analysis. Amazingly, extended mean value theorem is what you use to prove this. And so it's a very elegant theoretical construct, but the application of it, engineers and STEM majors love because it's simple to apply. Now let's look at a few others. What I want you to do is practice with this technique and use it to good health, so to speak. And this will be one thing you won't forget. So now let's try another one. Got several examples here. So we have the limit. Here's a one-sided limit. X approaches 0 from the right of e to the x minus 1 plus x. And also remember, ladies and gentlemen, just because you use L'Hopital doesn't mean that you're going to actually get a bona fide limit. I mean, if the limit doesn't exist, that's okay too. L'Hopital is not, a magic wand. It doesn't make the limit exist. It just tells you when it does in I guess, a more efficient way, as long as you have C1. Now, when you look here, notice this is a one-sided limit, so we're approaching from the right in this case. Right now, we're not really using that, but maybe eventually we'll need to use it. We'll just see. Who knows? These problems are constructed so they actually do work. And of course, if you're doing a calculus 1 problem and you're like, okay, well, this has a 2-part answer. I mean, if I'm approaching from either side, I get 2 different results. And so, of course, the limit doesn't exist. So now when we look at this, again, we let x approach 0 from the right. So this gives us basically an e to the 0. So this is like an e to the 0 minus 1 plus 0. And then, of course, we have 1 cubed. 1 cubed, 0 cubed. 0 cubed. And of course, this is just 1 minus 1. So this just gives us a 0 over 0. So e to the 0 by definition is 1, 1 minus 1. We get indeterminate. So now we go back here and say, well, these are nice in C1, at least in this neighborhood of 0. So we'll apply L'Hopital. So let's do it. So L'Hopital, limit as x approaches 0 from the right. Of course, e to the x is its own derivative. And then, of course, the derivative of -1 is 0. And of course, the derivative of -x will be -1. And then downstairs, we just get 3x squared. Now, if we check it out again, because we're thinking, all right, well, are we at a good stage? Well, we check this and we let x approach 0 from the right. So again, we get a e to the 0 minus 1, which is going to be 0. And then, of course, if we substitute 0 downstairs, we still get the indeterminate form. We still have C1 in tow. So this is what I was saying. We again have the hypothesis of L'Hopital. So we're saying, okay, we'll apply it again. You know, we didn't really, you know, fall off the bridge here. We're still in good stead. We can use L'Hopital, so we're going to reapply. So this gives us the limit as x approaches 0 from the right. Of course, now the derivative of e to the x is just e to the x. And then, of course, we have, well, that looks like a kind of, e looks a little bad. Let me write it so you can actually see it. There we go. And then, of course, the derivative of 3x squared is 6x. We like the simple problems. Now when we look at this, we're thinking, okay, what does L'Hopital's theorem say? Well, now, of course, we have an infinite limit. We're like, okay, so remember, we're approaching 0 from the right. And so, of course, we basically have division by a number that's essentially 0, and that defines a vertical asymptote. And the sign is positive. So this diverges to infinity. That's just an infinite limit. That's Cal 1. That is some of the most elegant arithmetic in calculus when you do infinite limits. And of course, you get that when you know the least about calculus. So this is back to our vertical asymptotes definition in calculus 1. So again, this diverges to infinity. Again, as x approaches 0 from the right, this approaches 1, but this approaches 0. That's the definition of a vertical asymptote. So we're done. So we're kind of cooked with this one. We don't get a limit, but we do know it diverges to infinity, which is better than, you know, just guessing. Okay. So that's an example where we get the existence of a limit here and we get the non-existence of the limit here. But when you think about this, you can stare at it for a little while and say, yeah, you know, that e to the x is just going to hang out all day long. And as we approach 0, you know, that the denominator doesn't look too inviting. So that's an expected result. So now let's look at another one. When you think about L'Hopital, you're thinking, in some cases, this might be like rates. When we start to get to infinite series and we're letting n pass to infinity, we'll use L'Hopital again to kind of investigate rates. And that'll be very, very good, especially when we do the limit comparison test. So this idea that you know, we may be working with sequences where you've got these discrete values, we'll just pass to the real valued function. And the beauty there is that if we can get the limit of the real valued function, we can back up. The problem is that the converse is not true. So we'll have to think about some things when we get to chapter 9 with the sequences of the infinite series to employ the L'Hopital. That is, as long as we think about the real valued function, you know, what is it doing? Can we back up? And so that's called restricting the domain, okay? And that's the beauty of real analysis that will allow us to pull some of this theory into sequences and infinite series, which will be very useful to us. So now we have the limit as x approaches infinity. Now we're going to flip it around. X cubed over e x over 2. So here's an example where we can actually use L'Hopital when we're looking at limits at infinity. And this is really important because we think to ourselves, as x becomes infinite, how do these functions compare rate-wise? And when you look at this, you're thinking, you know, the e to the x is really a powerful function. It grows very fast, very rapidly. And we would think much more so rapidly than x cubed. So let's apply L'Hopital. So now when we look at this, as x becomes infinite, x cubed clearly becomes infinite, and e to the x over 2 becomes infinite. So this is just L'Hopital with the second form of indeterminacy. And so, of course, C1, I mean, these functions are defined for all real numbers. So we don't have to worry about, you know, the C1 giving us a problem. So we can apply L'Hopital. So this one's like, kind of seems like we know what the answer is, but let's just see what L'Hopital tells us. So when we apply the derivative, we get 3x squared. And then, of course, the derivative of e to the x over 2 is just 1/2 times e to the x over 2, just taking the derivative of the power. So 1/2 e to the x over 2. So if you like, when you look at this, you can just keep everything right in the numerator and denominator. Don't worry about factoring anything right now. We'll just kind of see what happens as we move along. Now, when we look here and we apply the limit again, of course, 3x squared will become large or infinite as x approaches infinity. And the same happens for 1/2 e to the x over 2. So we still have the indeterminate form. So we can apply L'Hopital again. So just go ahead and keep all the numbers right in the numerator. No need to factor right yet. So this will be a 2 times a 3. So 3 times 2 x. And then we'll get another copy of 1/2 times 1/2 e to the x over 2. Okay, well, if we think about letting x, do we have a limit? X passes to infinity. Again, 6 times x will get infinitely large. And of course, 1/4 times e to the x over 2. Doesn't matter if we multiply by a positive number, we're still getting infinity. So we still have the L'Hopital hypothesis. So let's apply L'Hopital again. So this will be the limit as x approaches infinity. So now we just get what, 3 times 2. And downstairs now we have 1/2 times 1/2 times 1/2 e to the x over 2. Now, if you like, you can bring all the riffraff out. So we have 6 divided by 1/8, the limit as x approaches infinity of 1 over e x over 2. Well, now if you like, this is just going to be, you flip it over, that's just going to be a 48. 48 limit as x approaches infinity of 1 over e to the x over 2. But of course, now the numerator is constant relative to the denominator that becomes infinitely large. And of course, that is just an asymptotic result. That is, as the denominator becomes infinitely large relative to the numerator, this particular function converges to 0. So we have 48 times 0, which is 0. So the idea here is, when you look at the initial problem, you're thinking that limit is 0 by L'Hopital. Why? Because the e to the x, upon differentiation, preserves its structure. It's always an exponential. However, the polynomial differentiates to 0. And so we would think that the relative rates of growth would not be the same. This is like big O and little o, which you're going to learn about in differential equations, talking about rates of growth of functions. But when you look at this, you can kind of predict the future and say L'Hopital is going to give us a limit of 0 because we're basically going to have a constant in the numerator and the non-constant expression in the denominator that becomes arbitrarily large. So this is something that you prove in calculus 1, and you should think about why this is true. Or you could just write this as e to the negative x over 2 and let x pass to infinity. And of course, that would still give you 0 because then you have what we think of as a decreasing function. So the idea here is that now L'Hopital can put to rest these kinds of limits, and especially in transform techniques, you will often have polynomials divided by powers of e or exponentials. And you can look at it and say, by L'Hopital, the limit is 0. This is a very, very important limit that comes up over and over in transform methods. So now we don't have to sweat trying to do this. We can look at this and say, well, we're good to go. Now, here's another example. This is a famous example from Calculus 1 when you did special limits. The limit as x approaches 0 of sine of 5x divided by tangent of 9x. Now, if you're in Calculus 1, then you have the special limit sine x over x as x approaches 1. You prove that geometrically with the squeeze theorem to be 1. And of course, that's going to be something that we're going to see again when we do infinite series and see how all of this meshes together, that we actually were writing down things that were correct. It's always very comforting to know that what we learned in the previous class is actually true. I mean, I always tell my students, I said, please investigate this. You know, I'm going to give you the truth, but I don't want you just to think that, you know, you read something on the internet, it's not the truth. I mean, I could say something and I don't expect you to believe me 100%. I always tell my students, go out and do your own investigation, do your own computations, verify what I'm talking about. And that's what's important. So when we take calculus 1, we're thinking, man, I can go back and do all those limits with L'Hopital, save myself all that algebra, even though L'Hopital can require plenty of algebra. So when you look at this, you're thinking, well, we could just write the tangent as sine over cosine and rig the limit, you know, sine x over x, get it and reciprocate it or whatever, the limit's still 1, and do it the old-fashioned way. And you're thinking, okay, I'm all right with that. But now we have L'Hopital. So with L'Hopital, we're thinking, okay, if x is approaching 0, then of course, as the argument of sine gets close to 0, sine is approximately 0, and the same for tangent, because tangent is sine over cosine. So this is indeterminate. And these are clearly C1 in the neighborhood of 0. We know tangent has all kinds of vertical asymptotes, but they don't exist at 0. So that's fine. So now by L'Hopital, we have the limit as x approaches 0. So now we take the derivative of sine, that'll be 5 times the cosine of 5x. And now the derivative of tangent will be what? 9 times secant squared of 9x. So now it's like we're doing our integrals, but this is so much easier. I thought students will be glad to see this. I've, you know, spent more time on the Weierstrass, but again, this is now a valuable technique that we will need in the sequel. So now we're thinking, okay, well, what's going on at 0? Well, now, again, we're in good shape. These two functions here, at least the cosine and the secant function here, the secant squared, are continuous at 0. So now we're thinking we can just pass to the limit by continuity. So by continuity, we get 5 cosine of 0, that is 5 times 0 is just 0, and then 9 times secant of 0, quantity squared. But this is just 5 times 1 and 9 times 1 squared, which is 5/9. Now, of course, You could have done this proof using the special limit back in Cal 1, but now by L'Hopital, the answer is quick and efficient. But that geometric proof that you do to prove the limit before, that is, this limit here is an excellent study in using the squeeze theorem. It's important. I mean, you talk about continuity and limits in Calculus 1, this forms the bedrock of what you do when you talk about differentiation and integration. So don't forget whence you've come, but now understand that you have new methods to actually effect some solutions. Now, another example that we used a lot in Calculus 1 was the fundamental theorem of calculus, part 1. So let's look at this. And then I'm going to show you an interesting technique using logarithms. Now, there's some fun problems. There's a fun problem in your WebAssign about the first calculus text, L'Hopital. There's a L'Hopital's rule, and it's got a lot of algebra in it. It's very doable, but you'll have a good time doing it. It's big time algebra, but extremely doable, like doing the Weierstrass, keeping up with all the fractions and things and the powers, but enjoy that. So now we have the limit, the numerator, we have the integral, indefinite integral 1 to x of cosine theta d theta. And downstairs we have x minus 1. So this was also a problem that you did in Calculus 1, utilizing techniques when you were talking about Riemann integration. So this kind of revisits that concept. So when you look at this and you're thinking, well, that's interesting, you know, I need the fundamental theorem of calculus to do this problem. So if we look at this and we let x pass to 1 from the right, we're thinking, okay, now we just basically have the integral from 1 to 1, which by definition would be 0. That is, as x gets closer and closer to 1, this integral by continuity would be 0. And then, of course, as we hit, you know, we define when the limits are the same, we define the definite integral to be 0. So it makes sense. And then, of course, if x approaches 1 from the right, the denominator is also 0. At least it converges to 0. So we get the indeterminate form. So again, you're thinking, all right, let's try L'Hopital. So we have the limit as x approaches 1 from the right. Now we take the derivative of the integral. Remember, this is just set up for the fundamental theorem. So the derivative here is just cosine evaluated at the upper limit. And of course, we don't have to apply the chain rule because the derivative of x is just what? 1. So by the fundamental theorem, this gives us cosine of x. So this part is basically d. I love teaching Cal 1, even though I don't get to teach it much. It's a beautiful course. We have, for instance, a to x, where a is constant, f of t dt is just f of x. That's what you prove when you do the fundamental theorem of calculus. You should know that proof. That is standard in Calculus 1, even upon the regular section. So you should know how to prove that. That's a cornerstone argument that any calculus student should know. So now we just get f of x, which is just cosine of x. Here the theta is replaced with t. Seem to be doing a lot of that today. And then, of course, downstairs, what do we get? We just get 1. Okay, so now we're thinking, well, how simple? When we look at this particular problem, we see that now by continuity, we can just substitute. Cosine function is continuous at 1. I mean, the limit exists. You know how your professor would say, well, if you can substitute the numbers and you get a real number, you're done. And that's basically continuity. You know, we live for it. I mean, it's such an fundamental concept. You know, when we talk about limits, you know, by continuity, we can do a lot of things. We like functions to be differentiable, but continuous is fine. So now by continuity, this will just be cosine of 1, and we're done. So L'Hopital opens the door to some nice limit calculations, which will use the fundamental theorem. Of course, you can extend this by the chain rule if both of the limits are variable. Again, that's a form of Leibniz rule, which you just tack on the derivative of the upper limit after you do the composition with the integrand function. So that's another thing that you could do with L'Hopital. Now, one example is that maybe you're working a problem and you don't necessarily have the infinity over infinity, or you don't have 0 over 0. So you're thinking, I need to rig this. And when I said before, oftentimes the application of L'Hopital is not correct because it's applied in a form that does not meet the hypothesis. So let's do an example that you actually used in college algebra, but at the time when I teach pre-cal, I do some limit techniques, but I can't do the calculus obviously, but I can manipulate things and say, okay, if we can make this look like this, then we can make this substitution. So that's what I do in pre-cal, but now we can fill in all the details that we couldn't do in pre-cal. So let's fix. What does it mean when we say fix? It's a constant. So we're going to fix R in the real numbers. So this is fixed. So this means R is constant. So you're thinking if you had, let's look at the following, but we remember back in calculus 1, if we had a finite number times infinity, that was just infinite. That's not indeterminate. I mean, that's easy. Or infinity times infinity. That's just infinity. I mean, huge times huge kind of thing. That's not indeterminate. Mathematically, that's not something we have to operate on, so to speak. But we might have something like a power raised to 0 or a power raised to infinity. We're like, what is that? Or we might have infinity minus infinity. That's not 0. We don't know because infinity is not a number. It's not like saying 2 minus 2. So when we get to situations where it's not clear, we say, okay, that's indeterminate. But let me show you a technique how we can rig this. So for instance, we might say that we set y, and I'll use this y notation for a reason. I'll tell you why. We're going to say that we have the limit as x passes to infinity of 1 plus r. Remember, r is a constant, so this is going to remind you of interest, like r being a annual rate of interest. So if we looked at this particular problem, and we see, oh, okay, x is passing to infinity. So this is like the previous result. We had e to the x over 2 downstairs. The numerator is constant. So we see that 1 plus r over x is really getting very, very close to 1, okay, because this is converging to 0. So we have quasi 1 raised to infinity. So this is 1 to the infinity. We don't know what this is. This is indeterminate. Indeterminate. So when we look at that, we can't just say, oh, that's 1. That's 1. No, that of course that's not right. That's like saying infinity over infinity equals 1. That's ridiculous. It's nonsense. So however, there might be times when you do a computation and, well, that's what I thought it was intuitively. Well, trust me, you got lucky. There'll be times when your intuition and the theory just jive together, but it's not always the case with limits. So if you're running out of time and you're just kind of throwing caution to the wind, that's fine, but don't count on it. So now what we want to do is to rig this so this fits the hypothesis of L'Hopital. So what we can do is use the continuity of the natural logarithm. So we want to use the continuity of the natural logarithm. So we can apply the natural log. So the natural log of y will be this limit, which is the natural log of the limit as x approaches infinity of 1 plus r over x to the x. But of course, the natural log function is continuous here as x passes to infinity. This is a continuous function. That is, this argument is positive. And so we can interchange the limit and the log function. So this will be the limit as x approaches infinity. We do this all the time in Calculus 1, but it just seems like you're just doing what you're told and not understanding it. So we have the natural log of 1 plus r over x to the x. And now, of course, we know that we're still stuck, but we can use the power rule for the logarithm. So this is the limit as x approaches infinity of x times the natural log of 1 plus r divided by x. Now, one more step, just some little bit of algebra smoke and mirrors, is just to write x as 1 over x. So we can say this is the limit as x approaches infinity of the natural log of 1 plus r divided by x. This is a standard argument which you will use many times, and just x to the minus 1. So now, if we look at this expression and we let x pass to infinity, then basically we have what is essentially the log of 1 and then 1 over infinity, which gives us 0 over 0. So this form now is the hypothesis of L'Hopital. So the key here is that if we have a form that we don't understand, we can try to rig, in this case, using logarithms. And this is a standard technique. You don't have to take advanced calculus to use this. You just need to know a little pre-cal. And if you know some pre-cal and L'Hopital's rule, you know how to do it. So now at this point, we can apply L'Hopital. We certainly have C1 at infinity. So now we have the limit as x approaches infinity. So now we just take the reciprocal. So we have 1 over 1 plus r over x times, well, the derivative here would just be negative r over x squared. You learn how to do that in Calculus 1. I mean, 1 over x, that's the easiest derivative to take. And then, of course, here we just get negative 1 over x squared. Now, the nice part about this is that all the problems go away. The x squareds absorb and the negatives absorb. So we get the limit as x approaches infinity of, in this case, now you see with all of this running around, we've got what? X squared absorb, negative absorb, and we're left with r divided by 1 plus r over x. So we have r divided by 1 plus r over x. So now when you look at this, again, all of this work, very simple, just applying calculus 1. And then you're thinking, okay, well, are we out of the woods? Let's apply the limit. As x approaches infinity, this is well defined. That is, r is fixed, 1 is fixed, and then of course, r over x just approaches 0 because r is fixed. So this is just equal to, by continuity, 1 plus 0, which is r. So now you're thinking, well, that was easy, and it was easy. I mean, that's why I do the Weierstrass first compared to Weierstrass. This is simple, and it's so effective. And now you're thinking, okay, well, the log, what does this say? What's a logarithm? Power of the base, except when you got to Cal 1, and then your mind was blown because it was defined as an integral, and you're thinking, this is crazy. Okay, the logarithm is a power of the base. So in this particular case, when we look at this, the power of e that actually equals y in this case is r. So equivalently, y equals e to the r. So now, equivalently, the limit as x approaches infinity of 1 plus r over x to the x. Sorry, let me make that into an x, not an r, is indeed e to the r. And this is basically what you use in pre-calculus when you discuss continuous interest. So the idea here is that we can often find limits using very systematic techniques that are not difficult, that don't require us to do a major analysis of sequences using the monotone convergence theorem. Now, we're going to talk about that in the next chapter, and it's very important, but we will often opt for an argument like this that's at least doable. Okay, you will always reinvent yourself as you move down the road and think about new structures. But what I want you to do is apply, like I say apply uh, in good health, so to speak. When you use L'Hopital, you just make sure that you have the hypothesis, which is not always very difficult to do, and then move it forward. But don't continue to apply it unless you have the hypotheses satisfied. So now all of that interesting limiting process back in college algebra has now been put to rest. And you know why you get the PERT formula, P times e to the RT for continuous interest. So enjoy these topics. Next class, we'll talk about improper integrals. And that's even more fun. So when you get to your transform techniques, there'll be instances, especially in probability theory. Some of you will take some probability theory. You'll have improper integrals. Improper integrals are just kind of out there. And we will do the basics. Just however, remember that there are different forms of improper integrals, like there are different forms of integral techniques, which you will see in later classes as you need to know how to do them. So this is where my former engineering students will say, oh, Professor Ron, we had to do this, or I have Jose Daniel Velasco, who's doing his PhD in computer science. He's talking about all this stuff he's doing in artificial intelligence, but his basis was in number theory, which set him up for his PhD work. And so he always used to say, oh, thanks for teaching us number theory, Professor Ron. That helped me understand all of this. I said, no, you just knew what you needed to do to get where you wanted to go. So this is going to be a technique that you're going to find to be extremely useful in the sequel. So I appreciate your attendance today. Let's enjoy this great weather. I'll post the solutions for test 2 and get some feedback for you. And so if you want to go ahead and start working on this, it'd be good. I know you got to get your homework done for the previous sections, but just know that these techniques will be very useful as we move forward in the course. So thanks for your attendance today. I'll send out invitations for office hours, conference hours. If I see you there, that'll be great. Otherwise, we'll see you at the next lecture. Everybody have a great day.